So what we've got today is this problem, like I said, is dealing with random. Sorry, I forgot to disconnect the audio. It is dealing with random variables. So we have two different, what did they call them? Two different stages of an assembly line. And we've got kind of the mean and not standard deviation, but variance. It's important to note that that's what they're using here. And then we've got the variance of the second stage. We want to find the probability that these two stages together take more than 50 minutes. So the first thing we need to do is figure out the total time for this to take place. So we want the mean time of x plus y, if I consider these two different random variables added together. Well, that's just going to be our two means added together. Stage 1 and stage 2 added up is 28 plus 17, which is 45. So on average, it takes 45 minutes. It could take more or less time. We need to figure out how that varies. So the standard deviation for x plus y is going to be the square root of the variances added. Now, I don't need to square these numbers because they gave it to me as the variance. So keep that in mind. That's one of those really tricky things. So if you did square them, then that might be where you got off. So it's going to be the square root of 9, which is just 3. So now for our model, we can remember, just think of this as a normal model. And it does say that both of these are normally distributed. So normally distributed and normally distributed. So that means a combination of them will be also a normal distribution. So 45 with a standard deviation of 3. So we can go from there. So we want to figure out if 50 is about right here, what's the probability it's going to take more than that time? And now it's a normal CDF calculation. So it's going to be normal CDF. And we need to find out what our lower bound is going to be. Okay, actually, I'm jumping ahead because I forgot we are using z-scores for this. So I'm going to calculate what the z-score is for 50 minutes. So 50 is the data point minus the mean, which is 45, divided by the standard deviation, which is 3, gives me 1.6 repeating. So I'll just say 1.667. All right, so now I know that that's going to be my lower bound, 1.667. The upper bound is going to be 9999. Of course, you're using the interface on this. You're not plugging it in with like commas. But of course, we're using a 0 and 1 as our normal, the standardized normal model. So that is what it should look like on your screen whenever you finish your normal CDF parameters plugged in. And it looks like it's going to be about 0.0478, just under 5% chance of it lasting more than 50 minutes. All right. So I imagine if you didn't get that, it's because you squared your 5 and your 4 because you thought that was a standard deviation. And of course, I'd give you a much wider standard deviation. All right. That's all well and good. So one thing I forgot to do, we took a test yesterday and I forgot to get our progress up here. I know that's what you guys look forward to every time we take a test. That's my bad. I will correct that. Don't you worry. We are going to see how far we've made it down the river. And that will be on Monday. So a million apologies for that. I know that just ruined your Friday. But we're going to look through, kind of get some basic understanding of kind of the key themes of chapter 18. If you have not read it, that's going to be part of your homework over the weekend. Hopefully you leave today feeling like you understand the basic idea of sampling distributions. That's what the chapter is called. So of course it's going to be related to all that. And of course we'll dig into more of like the nuance of the topic on Monday and Tuesday. So I'm glad we did the bell work we did today because we had to use the normal distribution. But just a quick review of this because I'll finish this slide and then I'll have something else to say. So a normal distribution needs to be unimodal and symmetric with no outliers. The distribution is centered on the mean and its spread is determined by its standard deviation. And the normal CDF function on our calculator allows us to calculate the area under the curve for a set lower bound and an upper bound. So of course, a lot of times it's the upper bound or lower bound is just infinite. So maybe it's this area under the curve stretching off toward infinity. Maybe we're interested in, between these two z-scores, and we can find the area. This is review. I know you guys know this, but also just to explicitly talk about it, make sure it's right at the front of your mind. So what I was about to get at was that this is the last chapter, at least the way I see it. This is the last chapter where we're jumping into some new content. Of course, the chapters after this is new content too, but what you're going to see, and I hope it feels the same for you, is that every chapter after this is really just, hey, let's repeat the same information over and over again, but we're going to look at it in different contexts. And once you go through like the first part of like chapter 20, I can't remember the actual chapter numbers, but once we start going through that, it will make a little more sense what I'm talking about. And you're really going to see, it's just another z-score calculation. It's just another normal CDF calculation. It's just another z-score, and so on. All right. So important that just conceptually you're right there with me on what this is all about. And this is what we're going to start with. Oh, dang, I forgot to change that. That should be 4 friends, because there's only 4 people here. So they went bowling, and here are their scores. What was the average score? And anyone is
95.
95, there it is. So the average score is 95. This is just to kind of set the stage already. This is our population. The population mean is 95. So now we're going to approach it a different way. And we're going to randomly sample 2 people and find the average. Now, with this, you can just pick 2 people randomly right now, okay? And I'm not super concerned with what random looks like for you. So you might have already picked your own and found your average between them. I'll pick Annie and Candace. They got 80 and 100. So their average is 90. So how close was it? That's not too far off. It's not awful, right? So it's not super interesting right now what the average of the 2 people are. So let's kind of go further into it. What are all of the random samples we could get? All right, so of course it's A, B, C, and D right here. So I just picked Annie and Candace, and their average was 90. What are some other combinations of people that could be grouped together as a random sample?
Annie and Byron.
Annie and Byron. And if you guys want to fill in the average as we do this, that's fine. You can probably do this in your head. But let's also think of all the combinations that are possible.
Byron and Candace.
Byron and Candace.
Byron and Dante.
Byron and Dante. All right.
Candace and Dante.
Candace and Dante. Any others?
Annie and Dante.
There it is, Annie and Dante. So we really found all of them. This is another brief aside, but what we have here is we have 6 possible combinations for a random sample. And the next one would be, this is for sample size 2. I don't want you to think this is a general approach to this. But if we have a sample size 2 and we added one other person, maybe Emily or whatever, then this grows by what we call triangular numbers. So we would go from 6 outcomes here up to 10. The next would be 15. The next would be 21. So if we had 7 people, we'd have 21 possible groups of 2. And this is very much an aside. You do not need to know this, but it's kind of fun math stuff. They're called triangular numbers because you can start with 1, and then your next triangular number is 3, and then 6, and then 10. And you can see the pattern here. We just keep adding the next integer to it, and then we get 15, and then 21, and you can see what's going on. So those are your triangular numbers. And just one more fun fact related to that. If this was Pascal's triangle right here, so now I'll replace that with 1, 1, 1, 1, 2, 1, and so on. Your triangular numbers live right along that diagonal. So we've had a lot of fun here. But let's jump back to some statistics. All right. Which this stuff is not statistics. It's just not the statistics that we're going to be focused on today. So the average between Annie and Dante would be 95, and between Candace and Dante is 105. All right, so these are all of the possible samples we could have from this population. First, we start off with a really simple case, because when it gets more complicated, you're not doing this by hand. This one we can do by hand. So of course, I have a number line with no numbers here. So if this was, let's start with 85, 85, 90, 95, 100, and then 105. So now we can plot these in a dot plot. I'll just do it real quick. So 85, we have 1 there, 90, 95, oh, we have 2 95s, and then 100, and then 105. So we picked this example because this does a really good job with a small population and a small sample size to show that we're creating what appears to be a normal distribution. So it looks that way. But it's important to understand what all these dots represent. And I'm going to keep coming back to this a lot because it's so important that you understand it. This dot right here represents a sample mean. It's an X bar from a sample. All of these are samples, X bar, sample means, I should say. And so is that one. So I could label them all, but these are samples that we could draw from the population. We get a mean of it, and then we are going to summarize just the means from our samples. It's from repeated sampling. Okay, so clear enough with this one, I hope. So now we're going to see an example where it gets a little bit more complex. These are the actual Unit 5 test scores from 50 students, which is all but one test. I just wanted to make a nice number. So there's 50 tests. All right, and what we're going to do is I want you to get a sample size of 5 and get the average. I want you to find X bar for a sample size when n equals 5. And the way you're going to select this is with a random number generator to help you as you're going through, and I'll kind of walk through my first steps of it. There are 10 scores in each column. So I know this is going to be 1 through 10 right here, and then so on down the line. All right, so that's going to help a bit. So just as a reminder, because we only used it a little bit in this class, but if you want to get a random number generator on your phone, on your calculator, you hit the math menu, you go over to probability, random integer, and then 1 through 10. Now I don't want the same number, sorry, 1 through 50. I apologize. I was thinking of something else. So 1 through 50. I don't want the same number twice. So I am trying to sample without replacement here. So I've got, for me, the very first one I got was 36. So I'll come down to 36. is going to put me 1, 2, 3, 4, 5, 6, right here. There's the 36th one. So then I can go through and pick another and so on and get the average of all 5 of those. All right. So I will pause. I will let you guys do that. And then actually, sorry to interrupt you. After you're done getting a sample of 5, I want you to get another X bar for a sample size of 10. And I want it to be a different 10. So you're going to get 15 numbers total, no repeats. And the first time I want you to have 5 numbers to get an average. The second time I want you to have 10 numbers to get an average. Okay, so now that we've added the dots from our n equals 5, what we can do is we can see, even with this, it should be clear enough that we are creating something that appears to be a normal distribution. Now, this is only only a few of the possible samples we could have taken. I calculated earlier, I think there's 1 billion different samples that are possible, and we found like 15 of them. All right, so no, on this one, there's not 1 billion, that's for the next one, sorry. So in this case, there's gonna be still millions and millions of possible samples, and we're only seeing a very, very small amount. But imagine that we did have every sample that was possible, we took it and we got the average of it. So just to come back to this, this would be a random sample with a specific mean, and we are plotting it. And then we got a different random sample, and maybe we ended up with that one, and we got a different mean for that one. So if we took all the millions of possibilities and got the sample mean for all of them, we would fill in something that would end up being like a normal distribution. All right. And that's one of the key things. If you read the chapter, of course, you're familiar with that. So what the sampling distribution here, and that's what we've created, what the sampling distribution can do is it can show us where the mean might be. Now, I'm very roughly approximating this. So from this distribution, I would guess the mean is somewhere in that ballpark, but for right now, it doesn't matter a whole lot if we're super accurate. So for n equals 5, the mean, so I'll just put the mean sub 5, is going to be about 25.75. I don't want to be overly precise with this, so I just said 25 3/4. And it might actually be closer to 26, but whatever. The point is that this is hovering around that value. So now what I want us to do, I'm going to clear everything. And I want you to do the same thing, but now with your other point, which was your sample size 10. All right, so. All right, I don't know if we're waiting on any more dots. All right, now this one just so happened to be maybe less informative than the other one was. So this can happen when we have this few samples. Imagine that we had 100 people doing this, or if I had you get 2 different samples of 10. So we're going to see theoretically what happens here. This one actually looks more spread, like there's more variability in the sample size 10 than there was in the sample size 5. But still, we can kind of see, I don't know, I'm superimposing what I know the normal distribution where it should be. And actually, it would probably look something more like this if I'm doing my math right real quick. it should look something like that, with a bunch of values filled in. Somehow all of us avoided getting anything in this range, which is very strange. So let's say that we had a lot of samples. We would see a lot of samples filling in right here, and just, this is randomness. We can't predict that it's going to happen this way if we only have about 15 samples taken. Okay, so that's why the more samples you can do, the better. And the bigger your sample size is better, because what we're going to find is that when your sample size is bigger each time, then you are more likely to average close to the true mean. And the true mean here was, I believe, right here, 25.98. Now, I don't know what the mean of our sample size n equals 10. I don't know. I might put it about right there at 25. But the mean, so 10, I might just, for fun, call it was 25. Okay. So sometimes these activities that are supposed to illustrate the concept, sometimes they backfire a little bit. And this one, I'm not sure illustrated it very well. But if you can follow along with this, if we did have a lot, we should see a lot more filling in right in here. All right, and we would see a lot more kind of a normal distribution of what's going on. So that is the idea of sampling distributions. But again, just to drive this point home even further, this dot represents 10 different people selected from the population. So we had a sample size of 10, and we got the sample mean from those 10 randomly selected people in the population. Each dot represents a sample mean. All right, let me erase all this and let's move forward, and we'll kind of debrief on what all this means. Okay, sampling distributions. Every time we take a sample, we get a different statistic. And kind of jump around a little bit, I'll move to this next one. Any given sample is generally going to be different from the population parameter, and that difference is a sampling error. Your book also refers to this as sampling variability, which I do agree with the book. That is a better term for it because it's a natural thing that happens. It's not a mistake. But I will say sampling error is what you're more likely to see just out in the statistical world. So understand, error does not mean mistake in this case. All right. A sampling distribution is going to be the distribution that results from all possible samples of size n. We get to choose what the sample size is, and the sampling distribution is going to be all possible samples, the statistics that we get. So in this case, the means. Now, keep in mind, we came nowhere near all the possible samples when we did our last two examples. There were millions to pick from, 10 billion, I think, for the last example, when you have a sample size 10. So many different things going on. But when we create this, if we had all possible samples, it would, and this is always true, not just generally true, this is always true, it will form a normal distribution, the sampling distribution. And it's going to be, the mean of it is equal to the population mean. So whatever mean we get here is going to equal the actual population, in this case, the population mean. We'll deal with proportions another time. So right here we have the standard deviation is of our sampling distribution is equal to the population standard deviation divided by the square root of n. All right, so just some general things there to keep in mind. These formulas both come from the AP formula sheet, and we'll talk about that another time, but you can find them there. And I think I have a note about the notation here. So we'll get back to that in a minute, but we'll come back to these formulas. The first thing I wanted to do is just kind of clarify with this diagram. If you have your population distribution, it might follow this model right here, a normal model. And then you do a sample. I'm going to take sample size 5, get the average, and I want to plot all of those. And this is the distribution we might expect for sample size 5. And then we might go back and do another sampling distribution with sample size 30. And notice how it gets narrower and narrower. The bigger our sample size is, the less variation in the data we would expect. Okay. And the reason for that, of course, your data is just going to be distributed however it's distributed from the population. But when I get the average, then it's highly unlikely I'm getting all, 5 people all from the tallest or the high end of this distribution. If I'm picking 5 people randomly, I'm probably going to get some people in the low end, people in the middle, more people in the middle, and then maybe someone on the high end. And then if I average all that together, it's going to come close to the true population mean. So again, if I took a different sample, I might get 3 this time from over here and then 1 in the middle, but then I get someone really low. And when I average it all out, then it still comes out to, maybe just a little bit above the mean. So these averages tend to push things closer to the middle. All right, and then of course, if it was sample size 30, of course, you might get a lot of different people, but when you average it all out, you're probably gonna have a pretty good cross section and your sample mean is gonna be right close to the population mean. Okay, so hopefully conceptually that's making sense. You're able to follow kind of the thought process. This just kind of superimposes everything. Notice they all have the same mean. It's just the variation that changes. All right. So now about the notation. If you read through the chapter, we have different things to expect if we're dealing with proportions. We're not going to talk about that today. So I will talk about that another time, and that's what I say here. So this notation is telling us that the population mean, and that's what that mu always represents, is the population mean or the model mean, but in our case, the population is equal to the average, the mean of our sample means. So X bar is sample mean. And so essentially we're saying the population mean is the average of the averages. So it's kind of this 2-layered calculation going on. So mean of means, which will kind of force us toward the population mean. Okay, now the standard deviation, again, we have this X bar, so that's still sample means. And what it is the population standard deviation divided by the square root of your sample size. Now, we could work with this backwards. Generally, we can work and we can figure out maybe what our sample, or there are cases where we can figure out what our, sorry, not the sample mean, but the standard deviation of our sample mean is. So if we could figure this value out, then we could work backwards. We know our sample size is, let's say it's 10. Then we could do the math and we could figure out what the population standard deviation needs to be. All right. Now, just depends on the problem if you're given the population or otherwise. Okay. I hope that was not more confusing. All right. This is just another, it's kind of a conceptual thing, not a lot of math calculations and stuff related to this. But sampling distribution mean should be equal to the population parameter. And it's our estimator. It's the best guess that we can make. And an unbiased estimator is one that, on average, is equal to the population parameter. So this one right here is unbiased because this mean right here is equal to the population parameter. All right, the biased estimator, we consistently get something that's off. Okay, and think about this, like where would the source of bias come from? It might be from undercoverage or a non-response bias, or just basically the sample doesn't match the population. So if we were trying to find the average speed of a human, and we only picked of an adult, let's say, and we only picked people on high school, college track teams, then of course we're going to get speeds that are way lower than the true average speed for a human. All right, so it might not be the best example in the world, but you can get it. So make sure that your sample, the sampling frame that you're sampling from matches the population as close as possible. All right. A couple things about assumptions and conditions. Again, this is almost directly from your textbook right here. So you'll find this again. Independence assumption. We must assume that all of the values are independent of each other. And a lot of times that's just an assumption. And if we want to check that one, if we want to make a comment about it, we might kind of just think through the situation. So if it's, we want to find the average speed that a car drives on the highway, and we sample from, during one specific time. And so maybe if we're sampling from 5 to 6 o'clock, and we're trying to find out the average speed on the highway, well, if you're following my thought here, that's not necessarily independent, because those cars are all going to be going about the same speed. You're not going to have people going faster and slower. They're all going to be maybe caught up in traffic and going very slowly. If you're sampling during one 15-minute time frame on the highway, chances are people go about the same speed at the same time. So those would not be independent. So my whole point there is just kind of think through the situation. Are these really independent samples, or are they kind of changing based on what other outcomes are? The sample size assumption, the sample size must be big enough, and we will have ways of checking this in other ways, but for now, we'll just leave it there. You need to have a big enough sample size, and they are assumed to be true, so you need to kind of maybe just think through, make sure that they are actually true for the situation. And the condition. Some of these seem like repeats, but the randomization condition, the sample must be random. And oftentimes, if you're trying to check that the situation they give you, so if they give you a prompt and you have all this writing and you're like, oh, here's my condition, it has to be random. Somewhere in there, you're going to see the word random sample. All right, so if you see that, you can say, okay, it was random, we're good, check. 10% condition. This is also going to be kind of another intuition thing. Consider what the population is and how big the sample is. And almost always this condition is easily met. So they're like specialized cases where maybe we could be close to that or over the 10%. But normally the population is so big that their sample is going to get nowhere near the 10%. And finally, the large counts. Remember, we learned this in chapter 17. So we have the large counts condition. And we can only check that large counts condition when we're working with proportions. We do have other means, other ways we can do this when we're working with means. Okay, so I know it's kind of a shotgun approach today, just talking about a lot of things from chapter 18, but this is kind of what we're going to end with. We have heights of males, and we'll say these are human males. It averages 70 inches with standard deviation of 3.5 inches. And we'll start off with a question we should all be able to answer. What proportion of males are shorter than 5 foot 6 inches? All right, so just without having to go through all the math, verbally, can anyone describe how we would solve this problem?
Convert 5 foot 6 inches to inches and find how many standard deviations it is away from the mean.
Okay. So the number of standard deviations away would be our z-score. So of course, yeah, that's a good start. This is really 66 inches. Find the z-score, and just as a reminder, because you'll need to use this quite a bit, that's going to be whatever your data point is minus the mean divided by the standard deviation. And we're using a model here, so we can use the parameters. Okay. So now, and I don't want to spend too long on this problem. This is review stuff again. Data point here is 66 inches. The mean is 70. And our standard deviation is 3.5. And now we can figure out that z-score. All right, hopefully everyone's found it. Anyone get something besides negative 1.14? Might even go further, 1.143. I hope not, or maybe I made a mistake. All right, so now we've got the z-score. Okay, so what's the last step? What else do I need to do?
Normal CDF.
There it is. So in this normal distribution, negative 1.14 might be in that range right here. And we want to find out how unusual is it to be 5'6" or shorter. It's always implied in these types of problems. Well, here it's not even implied, actually says, or shorter than. But sometimes it's implied, like, is this an extreme value? And the question is really, is that value or a more extreme value unusual? So now you can hopefully set up your normal CDF. As soon as you find the answer to that, you can write that on the screen. I'll just put equals right here. You can, someone can write it there. Okay. And that is the right answer. It's a little bit hard to read that one, so I'll just write it off to the side. But yeah, we had the right answer. It's 0.12. I believe that's a 7. So there we go. Everyone should have that. And so this is our final answer. And what this is answering, it says, what proportion of males are shorter than 5'6"? Well, 0.127, or you could say 12.7%. All right, all well and good. This isn't the new stuff yet, but I wanted to establish, here's what happens if we're working with the population distribution. Now, or if you wrote over a little bit, but now we have a sampling distribution for heights of males, and we have a sample size of 5. So the first question is, what's the standard deviation of the sampling distribution? Does anyone remember the formula we have to use to find the standard deviation for a sampling distribution?
The standard deviation divided by square root of the sample size.
There it is. So the population standard deviation divided by square root of n. So you guys can plug that in. And come up with the answer here. There it is. And I'll add that decimal. Okay, actually. Good. All right. 1.565. And when we compare this to the original, it's smaller. Of course, it's going to get smaller. It's divided by the square root of the sample size, so it's going to get smaller. But just to show this, I can't emphasize this enough. Your population distribution might look like this, but your sampling distribution is going to look more like this. And again, just to reiterate, when I take an average of 5 males and get their height, the average of 5 males is going to be closer to the population average than any one person's height. Okay. Now, would a sample mean of 71.2 inches be unexpected? And what I want to do is I want to figure out what proportion of the sample means fall above 71.2 inches, because the overall average is 70 and 71.2, so it's going to be a z-score calculation. I'll just talk through this one. So 71.2 is maybe our specific sample mean that we got. Was that an unusual one to get? How do we find out? Well, let's do some calculations. If the population mean is 70 and the sample standard deviation, the sampling distribution standard deviation is 1.565, then I can calculate that. To get 0.767. All right. So there it is. There's our z-score. How unusual is that z-score? Well, I can figure that out by asking, all right, if my z-score for the sampling distribution is right here, 0.767, how many samples would be above that? All right, hopefully you can figure out how you'd approach this. So I'm trying to figure out how I want to phrase this real quick. So as soon as you get the proportion of cases that are above that z-score, you can just go ahead and write it there. I didn't give you much space, sorry. Okay, and there it is. So it looks like 22.2% of all cases, and I'll draw the normal distribution one more time. So from here, wherever that 0.767 is, this represents 22.2% of all cases. And my outcome from this might be, well, the fact that 1/5 of all cases are going to be above that means it's not super unexpected. It's not common, but it's not that rare. So is this unexpected? The short answer I would say is no. All right. So now we're going to do one last thing with this. All right. And again, I'll just get rid of this 0.767. Would a sample mean of 71.2 be unexpected if the sample size was 30? All right, so we need to go through this process one more time. In fact, I'm going to maybe not walk through it with you, but we'll walk through it at the end. So I'll let you try and figure out how you'd answer that. Okay, so some of you might be done. I apologize if you're right in the middle of doing some calculations, but I just wanted to ask, what anyone can respond. How did you guys approach this question?
I first found the standard deviation for the sample.
I'm gonna kind of add some notes about what you're saying.
Okay.
As you say it. So the first thing you did was found the standard deviation for the sampling distribution.
Yeah.
And what
And
was that?
that was 0.639.
All right, 0.639. Hopefully everyone knows how to find it. I'll just do this for completeness sake. The population standard deviation divided by sample size, which is 30. Square root of it.
All right, then I found the z-score. I plugged that into equation for finding the z-score.
Okay. So go ahead, fill in, or you can just tell me what what numbers you used for your z-score calculation.
I did 71.2 minus 70 over 0.639.
And your answer there was?
1.878.
All right. And then what?
And then I plugged in that into normal CDF with 1.878 as a lower bound and infinity as the upper bound. And I found that about 3%.
Okay.
3%. Yeah.
Okay, so I'll just put 0.03. I'm assuming 0302. Okay, so that's good. And that's good. That's exactly what you should have done. So hopefully everyone was able to kind of follow that same process, come up with the same answer. And just one last time, all of these data points that make up the sampling distribution are means, and this is going to be a sample mean with 30 in the sample size for each one of those dots. We're not seeing the dots, we're just seeing the model that's created, but you can imagine a lot of dots are what's making that model. Okay, so knowing that, it would be very, very unusual. In fact, only 3% of the time would you expect to find 30 random males, get their average height of all those 30, and then find that it's 71.2 inches, almost 6 feet tall. So most of the time it would be lower than that. So in this case, I'm going to go up to the top right where I have this. In this case, our distribution would probably look more like this. So 71.2, if I mark where that is, let's just say 71.2 is this blue line. All right. Now in our population, 71.2, right there where it intersects with the population, 71.2 isn't really unusual. All right, but then when I have a sample size of 5, that's this one right here that I'm highlighting again. There, it's a little more unusual to find something that 71.2 is the average of 5 people. But then when we get to the sample size of 30, it's just incredibly unlikely to find an average that high. Okay, so hopefully just visually that was making sense. Let's wrap this all up now, and that'll be class for today. Hey, we got 30 minutes to spare. Okay, so I posted a video on Canvas today, and I do really want you guys to watch that. I think it does a good job of just going over the same content, but it gives you different scenarios, lots of real world applications. Really good way of kind of reinforcing the ideas we talked about in class today. Read chapter 18 if you have not already done so. Okay, Monday and Tuesday, we're going to get into the nuance that happens whenever we're dealing with proportions and means. So that'll get started. And then the worksheet, I posted a PDF worksheet. The only thing you'll need to do is, like always, there's one question in particular I want you to respond to in a text file. So, but there is a worksheet that kind of goes through some stuff we did like in class today. All right, so that is all I've got for you. If you've got questions or anything else, you can stick around. Other than that, have a wonderful weekend.